Hello, and today we're going to practice a little bit about electrochemistry. Now, looking at this can be a little daunting if we were posed a question with all these blanks to fill in. So, what we're going to do is not going to even worry about all these blanks. We want to figure out what's going on. So, if you're ever given an electrochemical cell, first thing you want to do is figure out where your electrons are coming from. So, we can look at our two half reactions where we have lead and lead 2 plus, and manganese 2 plus, and we're given their standard reduction potentials. Now, whenever you have an electrochemical cell, you always have to have a reduction reaction and a oxidation half reaction. So what we're going to need to do is we're going to need to change one of these two reactions to become an oxidation reaction. And when we do that, we're going to change our standard reduction potential into a standard oxidation potential and change the sign. So when we do that, we need to consider, all right, well, what if we changed lead around and we made this a positive 0.13 volts? Well, if we added those together, we'd end up with an overall negative value, meaning it would be non-spontaneous. So you always want to change the one that will give you either the highest positive value or at least one that gives you a positive value in general. So if we were to change the lower one, this would allow us to get a positive 1.18 volts. And when we do that, that will allow us to figure out where our electrons are coming from. So if we go ahead and say we flip that reaction, we get manganese yielding manganese 2 plus 2 electrons with a standard oxidation potential of positive 1.18 volts. And now that we know where our electrons are coming from, I'm going to go ahead and fill out some more information here. So from our manganese, we are producing electrons. That's going to flow through a wire down through our lead electrode, and it's going to be interacting with our lead 2 plus. Now for our lead 2 plus, this is going to cause it to plate onto our lead electrode. So our lead will plate onto this lead electrode. And as the reaction goes forward, our manganese is going to corrode. Now, one of the other things that we can look at is we can write out what our cell notation would be for this. So we're going to start with where our electrons are starting from. We're going to follow the path of the electrons. And so we're going to start off with our manganese. Then we go through a phase change. So we're going from solid to liquid. So we're going to draw a single line. Then we go to our manganese 2 plus, or if you want to put manganese sulfate, either way is fine. Then we go through a salt bridge. So now we can have a double bar. Then we finally get to our lead nitrate. So either put lead nitrate or we can put Pb2 plus. And then finally we end with our final electrode, our lead electrode. So now we have our cell diagram, and I guess for some definition's sake, we always know if we are starting with our electrons, this is the anode, and it flows to our cathode. All right, you always want to spell out AC, so A for anode, C for cathode. All right, so now that we have all that figured out, we should be able to answer most of these questions pretty easily. So when we try to figure out what is the cell potential is just going to be the summation of these two values. So we're going to do negative 0.13 plus a positive 1.18, and when we add that together, we should get When we add that together, we should get 1.05 volts. When we try to figure out what's being oxidized, well, we can use our half reactions here to figure out what that is. So this is, the top one is our reduction reaction. The bottom one is our oxidation reaction. So we can just look at what is the reactant of our oxidation reaction, and that is what is being oxidized. So we know it's going to be the manganese. Then we'll look at what's being reduced. Again, we'll look at our two reactions. We have our reduction reaction here, so we're going to look at the reactants. So it's the lead 2+, or Pb2+. When we're looking at our flow of electrons, we're starting at the manganese, and then we're going all the way around. So we're starting from manganese, we're going all the way down through our lead electrode, and we end once we get to this lead 2+, right at the surface. So that's where our electrons are going to be flowing from. Now the electrode that's being consumed is the one that is providing the electrons as well, and is turning into our cations. So the manganese is being consumed. And then the lead electrode is what is being plated on, and it's being plated with, in this case, lead. And then finally, we need to figure out where everything is going in our salt bridge. So we can have potassium plus, chlorine minus. So as this reaction occurs, we are generating some manganese 2+. In that case, our Cl-, our anion, has to go into this solution. And on the other end, we have our lead 2+ being plated, so that's leaving the system. We have some extra NO3-. So to counterbalance that, we're going to need our cation to go into this solution. So our potassium plus in our salt bridge is going to migrate towards the lead nitrate solution. All right, so let's go ahead and look at another question here. Given the following reactions, which metals can oxidize zinc? So we need to figure out what we mean by oxidizing zinc. We're given a half reaction here with zinc, but this is a reduction half reaction. So for oxidizing zinc, what we need to do is we're going to flip this reaction. We're going to trade the products and reactants. So we're left with zinc, and then we'll actually have an oxidation half reaction. So when we do that, we get zinc yielding zinc 2+ plus 2 electrons with a standard oxidation potential of a positive 0.76. So just changing the sign on the reduction potential. All right, so now we need to figure out what can oxidize that. Well, what can oxidize this is whatever reduction reaction is going to give us a positive value when added with this standard oxidation potential of positive 0.76 volts. So if we add the calcium to it, we'll end up with a negative value still. We'll end up with a -2. So that's going to be non-spontaneous, so that reaction is not going to go through. The zinc will give us a 0, so it doesn't really do much of anything. It's essentially at equilibrium, so not much will happen. But if we look at either of these other two reactions, if we have lead 2+ or iron 2+, even though they're negative values, if we add them to the positive 0.76, we end up with an overall positive value. So those reactions would be spontaneous. So the lead 2+ or the iron 2+ will oxidize zinc. And we're given one more follow-up question. Which metal or ion gives the highest standard cell potential with zinc? Well, looking at this, we want whichever one's going to give us the highest positive value. So in this case, our lead 2+ is the most positive or least negative value. So that's one we're going to be using. So when we look at that, we'll have lead 2+ plus zinc will give us our highest cell potential of positive 0.63 volts for this given data set. Anyway, I hope this was a good review for you, and look forward to seeing you in the next video.